Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn about the vestigial sideband modulation. So in the previous video, we learned about the single sideband modulation. And we have seen that in case of the single sideband modulation, either lower sideband or the upper sideband is transmitted. But this scheme is well suited for only speech signals, which does not contain any DC or the low frequency components. So if the signal contains DC or the low frequency term, then for such signal, it is difficult to generate the SSB signal. Because if there is a no gap between the two sidebands, then we required a filter with a sharp cutoff. And in reality, all the filters have some roll off. And therefore, it is not possible to eliminate one sideband completely using this filter method. And we have seen that even if we use the phase shift method for the SSB generation, then also we will face some difficulties, because in such case it is impossible to build the ideal Hilbert transform block, and only approximately it is possible to design this Hilbert transform block, and such approximation also works for only speech signals, which does not contain any low frequency or the DC component. Moreover, as the message signal bandwidth increases, then it becomes difficult to design a circuit which provides a minus 90-degree phase shift to the entire baseband signal. Therefore, for a signal which contains DC or the low frequency components, it is very difficult to generate the SSB signal. And therefore, this type of modulation scheme is only useful for the speech signals. So in such case, where the signal contains DC or the low frequency component, like the signal which is shown over here, it is easy to generate the DSB-SC signal. But if you see, then the bandwidth required in case of this double sideband modulation is 2 times the message signal bandwidth. And whenever we are talking about the wideband signal like a video signal, then it is very difficult to compromise that much of bandwidth. So for a wideband signal like a video signal which contains very low frequency components, this SSB or this DSB-SC is not a ideal solution. So in such case, we can use this vestigial sideband modulation. So this vestigial sideband modulation is a compromise between the SSB and the DSB-SC. And if we talk about the generation of this VSB signal, then it is relatively simple compared to the SSB signal. But on the other hand, it requires a little more bandwidth than the SSB signal. So if we compare the three schemes in terms of the bandwidth, then this DSB-SC requires the maximum bandwidth. On the other hand, this single sideband modulation requires the least bandwidth, while the bandwidth required for the VSB is typically 25 to 30% more than the SSB signal. So as shown over here, if we see the output spectrum of the VSB signal, then in this vestigial sideband modulation, some portion or the vestige of the unwanted sideband also appears along with the desired sideband, and that's why it is called the vestigial sideband modulation. So in case of this VSB modulation, instead of completely rejecting the one sideband, it is suppressed using the filter with the gradual roll-off. And in this process, some portion of the desired sideband also gets filtered out. But we will see that if the filter is designed properly, then at the receiver, still it is possible to recover the message signal. So in case of this VSB modulation, we do not need a filter with a sharp cutoff, and hence the generation of this VSB signal is relatively simple. Moreover, this scheme can also be used for a signal which contains the low frequency components. So in this scheme, first with the help of the balance modulator, we can generate the DSB-SC signal, and then by passing that signal through the VSB shaping filter, it is possible to generate the VSB signal. So let us briefly talk about this VSB shaping filter, and let us see what should be the characteristic of this VSB filter. So this is how the response of the ideal VSB filter should look like. So as you can see, it has a flat response in the frequency range of Fc plus Fv to Fc plus B, and there is a gradual roll off from Fc plus Fv to Fc minus Fv. So here this B is the bandwidth of the message signal, and this Fv is some frequency which is much less than B. So using the balanced modulator, when we generate this DSB-SC signal, then there will be a one sideband starting from FC to FC plus B, and the one sideband will appear from FC to FC minus B. So as you can see, because of this type of frequency response, some portion of the desired sideband will also get filtered out. While from FC to FC minus FV, some portion of the unwanted band will also appear in the output. That means if we see the total bandwidth of this VSB signal, then the total bandwidth is equal to FV plus B, where this FV is some frequency which is much less than B. Alright, so now let us see the second desired property of this VSB filter. And to understand that, for a simplicity, the response of the VSB filter is normalized. So in this roll-off region from Fc plus V to Fc minus Fv, if we take the two frequencies which are equally spaced from Fc, then the summation of their magnitude response should be equal to 1. That means here this Fc minus F1 and this Fc plus F1 are the two equally spaced frequencies from Fc, and at these frequencies, if we see the sum of their magnitude response, then it is equal to 1. That means here this Hi of Fc minus F1 plus Hi of Fc plus F1 is equal to 1. So this is the desired property of this VSB shaping filter to recover the message signal at the receiver. And once we talk about the demodulation, then it will get more clear to you. So this is how the frequency response of this VSB shaping filter should look like. Now here, after this Fc plus B, the filter can have any arbitrary response. And actually, we are not concerned about that response, because here our message signal will be from Fc to Fc plus B. So beyond that range, the filter can have any arbitrary response. But in our region of interest, the filter should have these desired properties. So if we have this balanced modulator and this VSB shaping filter with the desired properties, then it is possible to generate this VSB signal. So after the balanced modulator, we will get these 2 times empty times cos omega ct. And let's say the transfer function of this VSB shaping filter is equal to Hi of t. So if we see the output of this VSB filter, then it is the convolution of this Hi of t and this term. Now if we take the Fourier transform of this term, then this 2 times empty times cos 2 pi fct is equal to m of f minus fc plus m of f plus fc. That means the message signal will get shifted by plus minus fc. And in the frequency domain, this convolution will become multiplication. That means this phi of VSBF is equal to m of f minus fc plus m of f plus fc times hi of f, where this hi of f is the frequency response of this VSB shaping filter. So this is our modulated signal. Now at the receiver, using the synchronous demodulation and using the proper low pass filter, the message signal can be recovered. So for the synchronous demodulation, the carrier signal at the receiver should be in same phase and the frequency as the transmitter carrier signal. Let's say at the receiver we have such carrier signal. So with the help of it, it is possible to demodulate the VSB signal. So let's say the output of this demodulator is equal to Vt. So if we see this signal in the frequency domain, then the multiplication of these two signal will shift the VSB spectrum by plus minus Fc. So now let us put the value of this 5 VSB from the earlier expression. So if we put the value of 5 VSBF in this expression, and if we write the first term, then in the first term we need to replace this f by f minus Fc. So if we put the value and if we write the first term, then we will get this m of f minus 2fc plus m of f times hi of f minus fc. So basically in this expression we have replaced the f by f minus fc. Similarly, to write the second term, we need to replace this f by f plus fc. And if we do so, then we will get this m of f plus m of f plus 2fc times hi of f plus fc. So now let us rearrange these mf terms and the high frequency terms. So after the rearrangement, the first term will be equal to mf times hi of f minus fc plus hi of f plus fc, and this will be the second term. And in fact, this second term is the VSB spectrum which is being shifted to 2fc. So with the help of the low pass filter, it is possible to remove this term. That means after passing the demodulated output through the low pass filter, only one term will remain. So if we want to recover this message signal empty, then this term, that is hi of f minus fc plus hi of f plus fc, should be equal to constant. So if that is the case, then the output will be equal to k times empty. And if this term is equal to 1, then the output after the low pass filter will be equal to empty. That means if the frequency response of this term is flat, then it is possible to recover the message signal. So let us also see the same thing in the frequency domain. So this is the frequency response of the VSB filter. Now in the frequency domain, actually this term is HIF, which is shifted by plus minus FC. That means in the frequency domain, if we see the response, then it will look like this. Now if this VSB shaping filter obeys one of the properties that we have discussed earlier, then after the addition of this to spectrum, we will get the flat response. That means for the VSB shaping filter, if the summation of the magnitude response of the two frequencies which are equidistant from the frequency Fc is 1, then in this region minus Fv to plus Fv, we will get the flat response. That means after the addition, if we see the overall response, then it will look like this. So as you can see, since this term has a flat response in the range of plus minus b, so whenever the message signal gets multiplied with this term, then the message signal will not get distorted. And with the help of the low pass filter, it is possible to remove the high frequency terms. That means whenever this hi of f minus fc plus hi of f plus fc is constant, then the design of this low pass filter becomes very simple and it is easy to recover the message signal. But suppose if the response of this term is not perfectly flat, then we need an output filter HOF such that after the multiplication, the overall response becomes flat. That means this output filter HOF should be equal to 1 divided by this hi of f minus fc plus hi of f plus fc. And the output filter should have this property in the range of plus minus b. So if this condition gets satisfied, then it is possible to recover the message signal. So on the second channel, we will take few examples based on this VSB filter design so that this concept will get clear to you. Alright, so in early days, this vestigial sideband modulation was used for the transmission of the TV signal. Because this TV signal was required a large signal bandwidth and it also contained the low frequency components. So for the transmission of such signal, this VSB was the ideal scheme. Now since the TV signals are the broadcast signal, so to keep the receiver design simple, the carrier signal was also transmitted along with the VSB signal, so that at the receiver, the demodulation can be carried out using the envelope detector. So that was the usage of this vestigial sideband modulation in the early days. So that's it for this video, and I hope in this video you got the general overview of this vestigial sideband modulation. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.